Hello everyone, welcome to this webinar where we are going to discover a coupled simulation between CFD analysis and artificial intelligence. In particular, we are implementing our own machine learning algorithm to do some predictions on CFD results. Thanks everyone for joining this webinar, and I hope you can hear me all right. Let's just check it, and we are ready to start with the presentation. Hold on a second. Let's just wait for the last attendees to come. Yep, maybe now the audio is coming up. Let's hope that. Just waiting for some confirmations. Is the audio coming? Yeah, here we are. So sorry for the delays. Okay, good morning again everyone. And let's start with the presentation. So during the presentation, you have a chat that you can use to interact with me. So you can ask a question, you can ask for a more detailed confirmation of what we are talking about. So there's a chat box right next to the right hand side. You can interact with me. Well, let's start by presenting myself and the company I'm working for. The company name is CFD FEA SERVICE. It's an Italian-based company founded in 2018. Our area of where we operate three main areas. We work in software development, in particular as far as engineering applications, both the mechanical and civil engineering applications are concerned. We have among the software developed a portal named Cloud HPC, which is somehow the protagonist of today's webinar. And then obviously we perform some consulting engineering activities in both mechanical and civil engineering applications. What is the Cloud HPC? Cloud HPC is a portal where you can rent hard resources to perform CFD and FEA analysis, but in general engineering simulations that are often highly demanding in terms of hard resources, and as a consequence it's difficult to have at all times and in all situations hardware in-house to perform this analysis. So on the Cloud HPC you can easily submit jobs on the cloud using a pre-configured server or cluster dedicated to engineering simulations. The benefits of the Cloud HPC is, well, first of all, that it is completely configured for engineering applications, so you can get everything ready to run for CFD, FEA, and several other simulation software. There are no subscription fees. Everything is built according to the actual use you have performed every month. And obviously there are no configurations or installations because everything is made available through a browser. We have several software available, among which I just categorized in this slide the software in terms of the functionality. So CFD software, we have OpenFOAM from the ASI or from the OpenFOAM Foundation, with the possibility of including customized solver. So if you have your own solver, it is possible to run it on the cloud HPC. We have FDS for very common in civil engineering applications for fire prevention, and we have Saturn, which is another alternative for CFD simulations, very popular because it's developed by EDF in France. As far as FEA analyses are concerned, we have Calculix and Codester and OpenRadios, just to give you a quickly overview. And they are all compiled with MPI, so it is possible to have a full parallelization using this software mentioned right now. And then there are plenty of other software, SU2 and other CFD solvers, very tuned for adjoint optimizations. We have several software to perform meshing, like Salome, CF Mesh Plus. We have Energy Plus, which can be used to energy equilibrium inside buildings, Shilab, Paraview for post-processing of data, TensorFlow, PyTorch for libraries that can be implemented for artificial intelligence. And today we will see how we made most of these tools available in an easy form. In terms of hardware that we're equipped with, currently the base hardware are AMD EPYC Milan, second generation AMD EPYC processors with a frequency of 3.3 gigahertz. And these are available for most of the instances you're going to perform on the cloud HPC. Or if you want a premium, let's say, a more efficient processor, you can use Intel Xeon Emerald Rapids, and soon also the AMD EPYC Turin. These processors, they both are capable of almost twice the computational power compared to the AMD EPYC Milan, because this is like the fifth generation of processors. On the cloud HPC, it's possible to execute several scenarios at the same time. There are no limits of the number of scenarios you can perform, so theoretically you can perform hundreds of simulations at the same time, and for every simulation you can allocate up to 192 physical cores dedicated to that specific simulation. We have on top of that some dedicated tools, we are going to mention that later in the presentation, which are specific workflow to simulate what? Well, turbo machineries, for example, there is TurboUp, valves, safety valves in particular, valve flow, car park for fire and smoke extraction. We have Bestgate for injection molding definition. So all of these are specific tools that can speed up your simulation, and in particular each of these tools is dedicated to one software. So in TurboUp, for example, you can use OpenFOAM. In TenuFAM, that's for gasket analysis, that is used with it's an interface for Codester basically. And then there are several ways to interact with the cloud HPC, and I want to stress the possibility to get real-time support because every software installed on our platform is a software for which we are capable and we have all the skills to use that software. So most of the times users can actually get a support not just on how to get their simulation performed quickly on the cloud HPC, but also on how they can set up correctly a case if a certain boundary condition is better or worse than another, and so on. So let's go now to our example of CFD and AI coupled simulation, and let's see what we have to do, what we want to do in order to perform these simulations. So I don't know how many of you are familiar with these tools, but maybe with CFD, most of you, but artificial intelligence and machine learnings are getting popular or commonly used in engineering applications just in recent years. So it's worth a while having a plan of what we have to do in order to train our own machine learning model and what we need to do in order to do this model. Well, everything starts obviously with a CFD analysis. In today's example, we are going to talk about turbo machinery, so a simple fan. So we need to set up a case in CFD analysis for a turbo machinery. That's the first step. Second, we need to generate a relatively high number of geometries, each of which represents a variation of the initial turbo machinery geometry definition. Then, for all this geometry, we have to perform a CFD analysis. This will create a certain input data that are going to be used to train a machine learning model. And we're going to see also what training a machine learning model means. From all these CFD analysis, we have to extract what we call lumped results. So we don't need to go into the details of the results, like looking at the pressure and velocity fields, but we just want to extract some lumped parameters, like for a certain given geometry configuration, we can get the absorbed power by the impeller, by the turbo machinery that we are simulating, or the efficiency, so how much, let's say, flow rate and how much head the impeller is generating compared to the absorbed power the impeller is using. So some parameters like these are to be calculated from the CFD analysis. Then we have to collect all these data, so the geometry variation and these lumped results, into an Excel spreadsheet basically, and give it to the artificial intelligence / machine learning. Machine learning is a subgroup of artificial intelligence that analyze big chunks of data, and out of this data that are given as an input, they can train a model which can be used then to extrapolate new results in order to perform optimization. So we have to provide the results of CFD analysis to the machine learning, train the machine learning method, and eventually extrapolate the results in order to obtain an optimized geometry of the turbo machinery. So we just the optimized geometry won't be any of the geometry that has been pre-simulated in this step, in the second step, but will be a new geometry given by the machine learning trained model. And then obviously eventually we will also run a CFD analysis to verify the extrapolation data made by the artificial intelligence in order to verify if this data extrapolated is actually consistent with the CFD results. Well, let's start because obviously everything can be done from scratch if you're a programmer, but we provide as CFD FEA Service a number of tools that can be used in order to speed up or make it easier for you to achieve all the steps we want to do in this phase. So let's start with TurboUp. TurboUp is a workflow that basically allows you to input a CAD file, set up with relatively few data, mesh and boundary conditions, and using these informations, the output is obviously the whole results of a CFD simulation, but on top of that, you get a CSV file with concentrated parameters, the lumped parameters I mentioned before, like flow rate, torques, absorbed power, efficiencies, and these are provided in CSV format, like an Excel file format. and they are monitored on control surfaces like inlet of the simulation, outlet of the simulations, on the impeller of the simulations. So this is a workflow that is already pre-configured in order to perform this type of simulation. So what we need to do is set up the geometry and set up the input parameters for this analysis. Another very good feature of TurboApp is the possibility of performing parametric analysis in two different ways. There can be parametric in terms of boundary conditions. So for example, you want to calculate a whole QH curve, so get the head obtained by the impeller at different flow rates that is going through the impeller. And so thanks to the parameterization, you can specify the several flow rates in meters cubed per second you impose at the inlet and obtain as lumped parameters in the CSV file the produced head by the impeller. That's one way of using the parameterization. A second way is the geometry variation. For example, you want to perform several geometry variations of the impeller, so monitor, for example, the angle of attacks, the diameter of the impellers, the number of blades on the impeller, and monitor how the head is varying according to these parameters. This is called geometry variation and can be performed automatically in TurboApp. So you just have to upload the geometries you want to simulate, and automatically will submit several jobs with the geometry variations. Obviously, these two parameters can be merged together. So I want to simulate like several geometry variations, so several geometries, and each of these geometries I want to extract the whole QH curve, so several flow rates. It will end up performing several cases, but we will get results for all these cases in Excel spreadsheet. Obviously, an input data we have to perform is a geometry variations. TurboApp is not able to modify the geometry. We must provide already TurboApp with a set of geometries. To do that, in-house, since we have licenses of Solid Edge and Microsoft Excel, we developed an internal algorithm that has a parametric Solid Edge geometry. And using basically a spreadsheet, it is possible to vary the parameters of the impeller, such as angle of attack, diameter, the gap between the duct of the impeller and the tips of the blades of the impeller, and the number of blades of the impeller, and so on and so forth. We have developed, let's say, a methodology that from Excel spreadsheets, thanks to a macro, automatically saves all the geometry variations of the impeller that are displayed over here. So basically, in this case, these Excel spreadsheets defines the angle of attack, impeller diameter, spout diameter, so the pipe diameter, and the blade number, and each of the rows in this table is then converted into a specific geometry. Each of these rows in this table can be classified as an X, as a sort of independent variable. So the geometry is actually represented by this set of parameters, which are converted thanks to the Excel spreadsheets, the Excel macro and the Solid Edge functionalities into a geometry. In here I'm mentioning a lot of times Solid Edge, it's just because we implemented this under Solid Edge, but the same methodology can also be applied to other free open source CADs like FreeCAD, but also commercial ones. So probably we need to, if you have specific questions about other CADs, just feel free to ask later in the chat or via email after the presentation. So once we obtain all these geometries, we can feed Turbo App, okay, with all these geometries, feed Turbo App with all the CFD setup, and eventually Turbo App will perform the simulation and will give us a table like this one, in which we get the results obtained for all the CFD simulations, but in a lumped coefficients. So for example, we get absorbed power of the impeller and the efficiency of the impeller. That's an example. And all this data, like impeller optimization version 1, it means that it refers to the first geometry, to the first set of parameter. Version 2, the second set of parameter has a second ID in here, the third set, fourth, 30, up to the 34th. So there is a link between the results produced by the CFD simulation and the set of parameter we started from in order to obtain the geometry and eventually to obtain the results of the CFD simulation. So at this point, we need to abstract a little bit to understand what we are doing and to understand what the artificial intelligence, in particular the machine learning, is going to do. So what we did is setting 4 parameters: angle of attack, impeller diameter, spout diameter, and a number of blades. We performed a CFD simulation and we obtained the absorbed power and the efficiency of the impeller. So we can see somehow the CFD simulation as a sort of a black box, as a sort of function that takes the input data of our geometry and using that function produces the absorbed power and the efficiency of our impeller. So if we were aware of what this function would be, we would be able to provide a new set of parameter, input, angle of attack, impeller diameter, spout diameter, and blade number, and obtain the power and efficiency without computing the CFD simulation. I hope I made this bit clear. It's like the CFD simulation was a black box, like a function that converts input data into outputs, and these outputs are the power and the efficiency. Machine learning, in our case, has the task to estimate this unknown function that transforms the input data into the power and the efficiency of the geometry represented by this input data. So the way we want machine learning to work is, first of all, we want to provide some computed points, so some parameters, x, we are providing to the function, and the output of the function for some known geometries. So we provide, let's say, some x values, and we provide the evaluated power and evaluated efficiency for those x values. And we used this data, so x, power, and efficiency, to train the artificial intelligence / the machine learning methodology. Once the train is completed, this means the artificial intelligence has estimated this function, we can provide the artificial intelligence with a new set of data, angle of attack, impeller diameter, spout, and blade number, and ask the artificial intelligence, can you estimate power and efficiency on this new set of parameters? In this case, we won't perform the CFD analysis, but the artificial intelligence will just calculate this f of the new set of input data, f of xn, okay, in order to estimate power and efficiency. There is a question. Exactly. So the question is, if we are creating a statistics model of the impeller by means of machine learning, and we use input and output. So yes, that's what we are doing. So the input data are the geometry representation, the parameters that are defined in the geometry. The output data are the power and efficiency. We create a statistics model which is generated initially by a certain set of CFD analysis that we are performing, and then the artificial analysis takes this as the statistical representation. Thanks to the machine learning, it will produce a regression. This is what it can be technically called. It calculates a regression models, which means evaluates the regression the function that transforms input data into power and efficiency. And once we have this estimated function, we can use to make a quick prediction of the results. Why we do that is because the prediction made with the artificial intelligence is instantaneous. There's no need. So we can perform, once we have performed this evaluation of the function, we can perform thousands of predictions in the time of a second or a few seconds. So this is why we want to do these statistical representations. Instead, if we were to perform CFD analysis of all the possible cases, well, it could take us, I don't know, hours or days of performing simulations. Instead, in this case, we are reducing the number of CFD simulations, and we evaluate and we use this reduced number of CFD simulations to perform a regression model. That's the real name we are doing. And then we use this regression model trained with artificial intelligence in order to estimate several other geometries. So as per what we said, we had to merge the results obtained by TurboApp with the input data of the geometry into a single Excel. The input Excel will be made of the geometry parameters and obviously the output data. The output data, they come from a CFD simulation. Obviously, the geometry parameters are those that we use to evaluate the CFD results. These are the input data, or the data under which we are training the machine learning methodology. There is another question. At the end, you got the response surface methodology, where you can grab the optimal design. Is that correct? Yes, that's what we are doing, or that's what basically we can generate with this methodology. So once we have these data, which are fundamental, because these are fundamental for the training of the machine learning, we can use a second tool named Claudia as our, let's say, artificial intelligence methodology. So we use the CSV file of the input data, and at the moment we also need to enter a prediction data set. So a list of row, another Excel basically, where every row represents a new data set point where we want to make the evaluations of the pressure, of the absorbed power, and the efficiency of the impeller. So the artificial intelligence will use input data to train the model and prediction to actually perform the prediction. And then we have to set the targets. So basically the targets, they want to tell you which basically the system must know that power and efficiency are actually the data we want the artificial intelligence to be trained upon. Okay, it's not the blade number is our target. We have power and efficiency, and so we have to specify that we have two targets. One is efficiency, and then we have the second target, and the other one is the power. This target name must be coherent with the field name on the input data of the Excel. Once we have done that, we can, let's say this is not really a simulation, but we can run this Claudia algorithm, which will train the method and at the same time will also evaluate the results on the predictions. Well, what do we get? It's quite simple because in here I generated this graph for the impeller. So I have all these black points, which are the CFD simulations that were actually performed on the impeller. And every point in here represents a different simulation, but obviously performed with a different geometry. In this graph, the x-axis represents the assault power, and the y-axis represents the static efficiency. Then we used all these black dots to train the artificial intelligence, and then to the artificial intelligence we sent more configurations that are those evaluated with blue crosses. So on the blue crosses, we didn't perform CFD analysis. We had trained the model using the black data input, and then we told the artificial intelligence to evaluate the results of the CFD simulation using the trained model. In our case, for this impeller in particular, we wanted to reach the highest possible efficiency with a maximum absorbed power of 200 watts. There were some other constraints in this project, but let's say that these were the two main constraints. So thanks to these, if you just have a look at the black dots, they are limited because it seems like we couldn't reach any geometry to have an efficiency higher than 60%, a static efficiency higher than 60%. Instead, with the blue dots, so with the extrapolation made thanks to the artificial intelligence, we could extend way more the efficiency. We almost reached 80%, 75, 80%. In particular, now I zoom into this region, which is the one of interest. In particular, a point very interesting was the artificial intelligence geometry number 96, which had an efficiency of approximately 76.5%. So taking these, we decided this was the best candidate point to suggest the impeller which matched the requirements. And what we performed was a CFD analysis using this impeller. And actually we discovered that the CFD analysis was not that far, was just a couple of points, efficiency points far away from this estimated efficiency from the artificial intelligence. So yes, the artificial intelligence was able to capture, let's say, the best results for our case, and the optimized results for our case, with a good approximation, I would say, compared to the CFD analysis. At the same time, we were able to do this optimization with just 34 CFD analyses. Okay. Then in here, the cost or the number of the hardware requirements to perform this artificial intelligence, machine learning, training and evaluation is like less than a tenth of a single simulation. Okay, so this computational cost is completely negligible compared to the cost of performing CFD analysis. And all in all, thanks to a combined CFD and artificial intelligence methodology, we performed more than 270 simulations. And if we had to compute everything with CFD simulation, it would be not critical, but at least costly in terms of also hard resources to be used on the cloud or remotely. But in this way, like with quite a limited number of CFD simulations, eventually we were able to get very good results and very optimized results given the initial conditions. So yeah, this is how you could use the tools mentioned. In particular, today we saw two tools. One is Turbo App, and the second tool was Cloudia. They both rely on Cloud HPC, so that's the third tool under which it was able to perform the CFD part, but also the artificial intelligence training and estimation of the results. All of these tools are available to download on our GitHub pages. I put here the link. So the top link is the tool where you can download the Windows executable, because they can be installed on Windows. The second is the same link, it's just shorter. So you just go to releases and then you download our tool installer.exe. In here, when you download this, you will get 5 or 6 extra tools, but among which you will find Turbo App and Cloudia available. And obviously, in these slides, I also report you with the informations to get in touch with us for info or Cloud HPC dedicated questions, and also the website, reference website, if you want to test our Cloud HPC, which is cloudhpc.cloud. This is the last slide of my presentation. I hope I made clear to you a possible way to use artificial intelligence, and in particular machine learning, and how can this be easily coupled with CFD analysis to perform optimizations. Surely we are going to improve our Cloud ER tool to make it easier to use and more, how can I say, easier to use, in particular when coupled with Turbo App and other CFD analysis tools we have available on Cloud HPC, but also like other software in general. I just suggest to get in touch with us via email or to follow our socials, LinkedIn, YouTube, etc., to get more information about developments and releases we're going to do to our software. If there are no questions, that's everything from me. I thank you all for being part to this webinar, and looking forward to seeing you on the next webinars. Bye everybody.